We continue the problem exam 2.1. We already proved alpha plus beta is 45 degrees because alpha plus beta is the inscribed angle ABC, and inscribed angle is half of the intercepted arc ADC. The measure of ADC is defined as the measure of the central angle AOC, because AOC is 90 degrees, so ADC is also 90 degrees. By theorem 2.2, we know ABC, the inscribed angle, is half of the measure of ADC, which is 90, half of it is 45. So that's how we proved ABC is 45 degrees, which means alpha plus beta is 45 degrees. And now we try to determine each of the angles, the measures. So first of all, we know M is we know DE is a perpendicular bisector of OC, because it's perpendicular and it's a bisector because M is a middle point, and all of these conditions are given in the problem. And by the corollary, we proved in first section, page 21, corollary 1.2. If we have a perpendicular bisector of a line segment, then any point on that perpendicular bisector is equidistant to the ends, so both ends of the line segment. So that means these two red line segments, DO and DC, are congruent. And also notice DO and CO are congruent because they're both the radii of the circle. So of course DO and CO are congruent, and the DO and DC are congruent. So this makes it an equilateral triangle. We know in the equilateral triangle, each angle is 60 degrees. So the angle DOC is 60 degrees. And notice this is a central angle. DOC is a central angle that's 60 degrees. That means this intercepted arc DC is also 60 degrees. And then let's see if we can find any inscribed angle of the same arc. Inscribed angle, then we look at this arc DC or CD, and then we find out this alpha is exactly, so alpha is the inscribed angle intercepting the arc DC. We already know arc DC is 60 degrees, so inscribed angle is half of it. That means 30 degrees. So that's how we find out alpha, that's 30 degrees. And then we know alpha plus beta is 45 degrees. That means beta is 45 minus 30, that's 15 degrees. So in this problem, we used a lot of things we learned. First of all, the inscribed angle is half of the intercepted arc, and the intercepted and any arc is the measure of the central angle. That's the definition. Okay, next we talk about the quadrilaterals inscribed in a circle. So if we have a circle, we may have a polygon inscribed in the circle if each vertex is on the circle, and the polygon is cyclic if is the same as that it is inscribed, and a circle is circumscribed in the polygon is also equivalent statement. Every triangle is cyclic, which means any triangle we can always draw a circle such that this triangle is inscribed in a circle. Well, next section 2.2, we're going to talk about a circle inscribed in polygons. So there are two different things. A polygon is inscribed in circle, so kind of like contained in a circle, or a circle is contained in the polygon. So there are two different things. If we look at this picture, we have a circle, we have inscribed polygon. We want to prove this theorem. a necessary and sufficient condition for quadrilateral to be cyclic is that the sum of the measures of a pair of opposite angles is 180 degrees. So if we look at the last slide, we know every triangle is cyclic, which means any triangle can be inscribed in a circle. What about a quadrilateral? How to prove? So what kind of quadrilateral can be inscribed in a circle? So not every. So if we are given a quadrilateral, a polygon, we may not be able to draw a circle such that all the vertices lie on the circle. So what is the necessary and the sufficient condition? So theorem 2.4 says if we have one pair of opposite angles, for example, if angle B and D add to 180 degrees, then we should be able to draw the such circle. We have two conditions we want to, two directions we want to prove necessary and sufficient. So first, let's see what such necessary condition is. So if the quadrilateral is inscribed in a circle, so we already have a quadrilateral that is inscribed in a circle. So first we have a circle, and then we pick 4 points, and we connect those 4 points. We get a quadrilateral, and we want to prove the sum of the measures of a pair of opposite sides is 180 degrees. So for example, we want to prove angle B plus angle D is 180 degrees. How to do that? So this can be proved by dividing this quadrilateral into two triangles. So if we connect A and C, we get two triangles, ABC and ADC. The angle B is subtending arc ADC, and the angle D is subtending the angle ABC. And of course, the total of these two arcs is 600 degrees, because one circle is 600 degrees. 360 degrees. So the sum of these two angles is 180 degrees. Because we also, so how do we get 180 degrees here? First of all, we know angle B by the theorem 2.2, inscribed angle theorem. Inscribed angle is half of the arc ADC. And angle D, which is also an inscribed angle, so the measure is half of ABC, the arc ABC. Because ABC plus ADC is a 360. Angle B plus angle D should be half of the total. So that's going to be 180. So if we want to write down the details, so the angle B is half of the arc, the measure of arc ADC. And also angle D is half of arc ABC. And this is just, both of them are implied by theorem 2.2, the inscribed angle theorem. So we want to find angle, because angle B plus angle D, when I say write down angle B plus angle D, I mean the measure of both is equal to half of. So if we add both sides, we add the left side, we have angle B plus angle D equals half of the right side plus the right side. So half of angle ADC plus half of angle ABC. And of course, if we factor out half of the half of one half, then we get arc ADC plus arc ABC. And we know arc ADC plus arc ABC, that's the full circle, which is 360 degrees, which means half of it 180. So that's how we get the angle B plus angle D. These two angles, we add them, we can get 180 degrees. That's one pair of the opposite angles. So similarly, we can prove angle C plus angle A is also 180 degrees if we connect B and D. In fact, we know we have proved before in one of the sections that the degree sum of a quadrilateral is 360 degrees. So AB angle A plus B plus angle C plus angle D is 360. If these two add up to 180, of course A plus C is also 180. Okay, so now the necessary condition has been proved. Now let's look at the sufficient condition. The sufficient condition says if the sum of the measures of opposite angles is 180 degrees. For example, if we look, we have suppose we have a quadrilateral EFGH. So we start with the quadrilateral. We don't have a circle. Suppose we don't have a circle yet. So EFGH is a quadrilateral. Suppose we know angle G plus angle E is 180 degrees, or angle E plus H. So if one of them is 180, the other pair is also 180. So just assume one of them. That would be fine. Suppose angle G plus angle E is 180. We want to prove we must be able to draw a circle that has all these four vertices on the circle. Suppose, well, how do we prove it? We use indirect proof. Suppose it's not cyclic, which means there's no way we can draw a circle such that all four vertices are on the circle. If we can't, we can at least, we know these 3 points we can draw a circle. So suppose FGH, through FGH we can draw a circle, but we cannot have E on that. And well, this is one of the statements we talked about before. Any triangle, suppose FGH is a triangle, can be inscribed in a circle. So you can think about how to prove that after as a review exercise. So this, we can guarantee 3 points on the circle, but not the 4th point. But we want to prove actually also guarantees the 4th point, because the condition that angle G plus angle E is 180 degrees. If we don't have this condition, we cannot guarantee this 4th vertex is also on the circle. So next we're going to do is assume this E is not on the circle, so we must be able to have we just randomly pick another, actually not randomly, we can extend one side, HE, intersecting the circle at E prime and connect F and E prime. Now we have this triangle, E prime, F, and E. And in this triangle, we can see angle E, the original angle E, FEH, is the exterior angle of this triangle. And we know the exterior angle must be bigger than the remote interior. So angle FEH is bigger than angle FE prime H. And again, we know in a circle, if we have inscribed quadrilateral, the opposite angles add up to 180. So E prime plus G is 180. And what's given? What we have given is angle E. Angle E plus angle G is also 180. So that means these two angles must be congruent. So we get a contradiction because we know E is greater than E prime. So in this case, if I want to write down the details, that would be by the condition given, angle E plus angle G is 180. By the necessary condition we just proved here, if we have inscribed a quadrilateral, so this FGH E prime is inscribed a quadrilateral. So E prime plus G is also 180. If both of them add G, we can get 180, which means E and E prime, these two angles are congruent, which contradicts the exterior angle theorem, because they cannot be congruent. E is bigger than E prime, so we get a contradiction. So that's why these two have to be the same point.